So we see some contrast in the image and how to understand that. So that should be our aim. And these are the prominent mechanisms to which contrast comes up in the sample. So the first is mass thickness contrast. It's actually very easy and straightforward to understand, and I mean it will be more or less a repetition of probably things that you already know. I would say it's very common sense to understand that. That's not a big deal. Then there is diffraction contrast. That's where probably we will have to maybe you will gain more information. I have a feeling that mass thickness contrast is something which you will easily grasp. And here we need to spend some detailed time, and we'll see how it goes. And then the phase contrast and Fresnel contrast. So these are the mechanisms, and we will try to understand each of them one by one. So let's go ahead. And in the next slide, yeah. So now we are trying to understand the mass thickness contrast, and that's why I have here a sample which has got variation in thickness. Here it is thin, here it is thick. Then there is variation in the mass. Here there is, let's say, more mass. Here there is less mass, because I have depicted by dark thing as something which is heavy, and by light as something which is light. Okay. And this is, I said, is a bright field microscopy. Assume it's bright field. For dark field, it will be exactly complementary. So we don't necessarily have to discuss the dark field contrast especially, but we'll only understand the bright field imaging, let's say. And what was the case? That in bright field microscopy there was that objective aperture which sits in the back focal plane of the objective lens. So no lens etc. is shown here, but the aperture is shown. In fact, this I took from this book. In that book they didn't explicitly mention about the apertures, but I put it myself for the sake of understanding. So we have the apertures, let us say, we have kept them. And what we said is that this is bright field microscopy. These are indeed bright field, okay. And we said that we will allow the 0S beam to go through, yeah, or the beam which is scattered in forward direction primarily. So we have put our aperture, and here please don't get confused in the following way. This is a little bit confusing, okay. So let me clarify right from the beginning. We are actually talking of bright field imaging where there is parallel illumination. So this schematic diagram tends to make you think that beam is falling here, then it is falling here, then it is falling here, like that. But please, this is just for the sake of understanding. So, in reality, it could as well be, in fact, it will be as if the whole region is being illuminated by a parallel beam. Yeah, yeah. In a way, you should understand it. Yeah, correct. So that's okay. Now, let us say that good. When you get confused, I will explain it first. And if you get confused, then we will discuss later. That's, I think, the best way, because we have to do something. Even to get confused, we have to make some action. Only then we can. I will try my best. If we get confused, we will clarify. Okay. So let's say the electron beam is falling here, and then there is scattering. Now, but here the scattering is not much, correct? Because it's, first of all, it is thin, and secondly, it is also light. So there is not much scattering, and most of the intensity remains in the parallel beam, in the forward beam, which was our original beam. This beam which was there, most of the intensity doesn't get scattered; it remains there. Yeah, this is common sense, correct? Now I have my objective aperture, and just I think here, if you read it at your leisure, there is some explanation as to how. So here it says that there were probably some number of, let's assume there were 50. Yeah, there were 50 incident electron beams. This is just for understanding. Of the 50, 47 managed to remain in the same beam. They don't get scattered at all. Here, the element composition is still light, but the thickness is more. So of the 40, 53 remain and 7 manage to get scattered. In this case, it's not only thick, it's also heavy. So 37 remain and the 13 get scattered. Now when I put a aperture like this, and I use only the rays which are between, objective aperture is of a definite thickness. So only those, aperture means like there will be, let's assume, 2 metal plates. So it will, and there is a gap between them, or there is a strip in which there is a hole. So the electron, so when I put that strip inside, where only through the hole the electrons will be allowed to pass through, rest of them will be blocked. Yes. So that is what is this aperture. So here, of course, this zeroth beam is still has managed to retain lot of intensity in it, and therefore this beam will be quite strong, isn't it? This is clear. That's why more number of electrons in it. Here it will be intermediate. Here it will be the weakest. Okay. Now, so this much is clear, is understood, isn't it? Now what we do, we imagine that this the whole beam is actually, it is not that the light is falling here. The light is parallelly falling on the entire area. Let us assume like that. And we know how do we form an image? Of course, there is somewhere in this plane itself there is going to be a diffraction. Diffraction is going to happen. In fact, there should be, where we put the objective aperture, there has to be a diffraction plane. And with that, in that diffraction plane, we are catching only the zeroth beam. That beam or that radiation which was more or less going parallel, correct? Just as we try to take that parallel beam. So we are taking that parallel beam because that's the place where the parallel direction. Okay, let me try to make it little more elaborate. Parallel beam falling like this. Then what will happen at this stage? Parallel beam will continue to go down. Okay, one direction. The diffracted direction will go something like this. The other diffracted direction will go something like this. Correct? That's what happens. Then I put a objective aperture here. Yeah. When I put an objective aperture, then all this much big parallel direction would have been concentrated into one spot, which will be first diffracted spot somewhere here. The one which went straight would be formed as a spot here. The one which went in that direction would be formed somewhere here. Okay, so this is clear. We saw that earlier many times, isn't it? Now I put my objective aperture. So all of that ray which was so big has been confined into 3 spots. So all of that ray has been formed into 3 spots, 1, 2 and 3. This is clear? And I put my objective aperture here like this. So this beam, the other two, they immediately got blocked. Only this one managed to pass through. Of course, it is this beam has become most condensed at this diffraction spot, which is what is diffraction. But here I am most efficient in also in selecting this one and blocking others. So I would better put it. After that, of course, it will get enlarged, and then in the image plane, in the first intermediate image plane, it will form an image which is perfectly alright. But I have managed to select only the zeroth beam. Correct? Is this understood? Yeah. Now, and then I get an image. Now you know that image, definition of an image is that to every point in an object, I have a corresponding point in the image. Correct? So, to every point in this region, I get a corresponding point in the image. To every point in this, I get a corresponding point in the image, like that. And because of this scattering which I explained, now this point is going to look, how is it going to look like in the image? Because in the bright field image, how is it going to look like in the image? This I think is now you have to answer. Please tell me, when I make an image of this sample by the technique that we just discussed about, how is this area going to look like? Whether it will have more intensity or less intensity? Less intensity. So you have understood, yeah? So that's all is all about mass thickness contrast. I think we can more or less close here. We will probably talk about some examples, but okay. And this is just a repetition. How is it this exercise? So far we were only drawing schematic and all that. So this is the condenser aperture and lens, and here is the sample which we put in, and this is the objective aperture, and this is the first intermediate image plane. Correct? So these are the 3 things which we also use to schematically discuss the whole thing so far, and that's shown here. Good. Yeah. Now there is one more case which has come up, and let's discuss it. And for that, maybe I will go back and let's think of an experiment where I have a sample like this. And the scattering will happen and I don't use any objective aperture. I don't use the objective aperture. I just make an image just like that. What will be the problem in that case? Because all the pardon? Yeah, means that this scattering happens, etc. We are not using. I mean, this mechanism of getting contrast, depending upon how much scattering has happened, that we are not using if we don't use the objective aperture. That's what is happening, isn't it? Because this thick region and heavy region will of course scatter, but we are not filtering out the scattered part. So what will happen when the image is again formed? These scattered beams also come back to that image and form an image there. So scattering happens, but these scattered rays again come back to the image and contribute to the image. So effectively, although they got scattered, they came back to the image again. So there won't be any contrast because of the fact that there was scattering, and that is demonstrated in this image here. So this is some biological sample which may have also been stained because some parts or components of the biological tissue they tend to absorb this stain, urinary stain or something like that. That's a heavy. So they become very heavy, and rest of the part doesn't do that. Now when I use an objective aperture, I get such a beautiful contrast. Yeah, because those parts of the cell which absorb that heavy element, they are heavy objects, so they will scatter a lot, and therefore they will appear dark. Correct? Now, if I'm not a good microscopist, then I don't make use of this mass thickness contrast, and so I don't use objective aperture to make an image, and therefore I make an image like this. I don't get as much contrast as I get here because of the reason that we discussed about. Yeah? So although scattering happens because our sample was stained, so there is a possibility to get good contrast, but because we didn't insert objective aperture, we are not utilizing the entire contrast of it. So this is an answer. Yeah. Now that was example from, let's say, biological sciences, and this is one example wherein we have, let's see what is the sample. Sample is epoxy filled with amorphous silicon dioxide nanoparticles. Now epoxy, as you know, is some kind of polymer. Of course it has to be amorphous, correct? So the matrix is a amorphous material, and then inside that are silicon oxide nanoparticles. Those are also told to be amorphous. So we have amorphous material as matrix and amorphous material as nanoparticles or inclusions in it. Yeah, that's our material composition, and we make a bright field image out of it. Now see that epoxy is likely to be some organic material, so it is a light element material, correct? And whereas this silicon oxide is in relative to the matrix heavy. So if we make one static image, we get a contrast like this. And you see here, normally a typical material scientist usually works with crystalline samples, and therefore he will never get an image like this, because some of the, even if the matrix was amorphous, if this, let's theoretically or just make an imagination, if these silicon dioxide nanoparticles were not amorphous but were crystalline, how would the situation have been in this image? It would have been same? Huh? It would have been same? No, it would not have been same, because we are going to talk of one more contrast mechanism, and that's what is the Bragg diffraction contrast diffraction. But we will come to that maybe later. Right now, however, it doesn't play a role because it's an amorphous material. There is no scope for diffraction contrast here. There is no, like my lattice planes are favorably oriented for diffraction or not favorably oriented for diffraction. That question doesn't come into play at all, and that's why that diffraction contrast, had these silicon dioxide nanoparticles been crystalline, then some of these nanoparticles would have looked much darker, some of them would have looked less darker. They might all have probably been looking more dark than the polymer, epoxy, but there would have been variation in the darkness of the silicon oxide nanoparticles had they been crystalline, depending upon their orientation to the electron beam and whether they are favorably oriented for diffraction or less favorably oriented for diffraction. But right now that question, that mechanism doesn't come into picture. The only contrast mechanism is the mass thickness contrast, and that's why I get this kind of, all the nanoparticles look more or less uniformly dark. If at all there is some variation in the darkness, that has to do with the size of the nanoparticles. Those which are small, of course, will probably look little less dark because they are small. I mean, there's more epoxy than the nanoparticles. So it's very odd. In fact, that's an example of mass thickness contrast. If my nanoparticle, which is heavy, would be small, that area would look more brighter in comparison to a neighboring area which would have a bigger nanoparticle, because that's a mass thickness in the bigger nanoparticle would be bigger, would be heavy. So this is clear. Now, I think this movie was working for some time, isn't it? Initially, so that was actually tomography experiment. That is, they tilted this sample inside the microscope. They acquired images at different tilts. Now, why that experiment was done, I will tell you that, because you would not do this, you would probably be very hesitant to do that. If the silicon oxide nanoparticles were crystalline, you would probably not do that experiment. Can anybody guess why one would not do that in such a mode? One would not use bright field microscopy images to make a tomography experiment in this case, had these silicon oxide nanoparticles been crystalline.
That will give some shadow.
Okay, so I will give the answer. Answer is following that. See, we are making the tomography. Aim of tomography is to reconstruct that image in a three-dimensional view. That's the aim. But and how do they? So they are going to sum up all these many images which they acquire at different angles. They are going to sum up and draw some conclusion regarding its three-dimensional shape. And during that, I mean, for this evaluation of the three-dimensional image, one assumption would be that, I mean, the intensity of each particle, let us say, should be directly related only to the tilt which they are making. Yeah? So had it been pure mass absorption contrast like this, then that assumption will hold good. But if these were crystalline, then even when, for example, I am oriented in such a way that I would have otherwise expected it to be looking less intense, but if it has to be let us say to be looking bright, but because it is satisfying the diffraction condition, if it is going to interfere, because this diffraction contrast, if it were to interfere with this mass thickness contrast, it would be difficult to interpret the three-dimensional tomography images that I make, and that was the reason why they would not make it with that. Okay, so is this sensible, isn't it? Yeah. Okay, good. So then we see one more example, and that is, so it is some, okay, this is a TM sample wherein we have, this is the polyaluminum nitride film grown on SiO2, grown on a silicon substrate, but this silicon substrate has the amorphous SiO2 layer and with a platinum titanium layer also here. Yeah? Now what are the contrasts that we are seeing? So here and here and here we see more or less uniform contrast, yeah, but the contrast is different. This is the most bright, then this is most dark, this is intermediate. Yeah? Now what and they are all uniform in the whole thing. So this has to do with the mass thickness contrast, which is the one which is dominant. I mean, this part is amorphous, this part is also amorphous, we know, and what the platinum titanium is, I really don't know. But in any case, at least we are not this term. That's why it's probably important, dominant. So even if it is crystalline or nanocrystalline, probably the mass thickness contrast, platinum and titanium, as you know, probably they are the heavy, one of the heavy elements, and their mass thickness contrast is at least dominant. So glue is some kind of carbon material, polymer again probably, it's light element, and therefore has a, this is a, which kind of image it must have been. Here the answer is given, but does it also fit into our logic or what we have understood? That a darker, a lighter, thinner material would look brighter in a bright field image, and that's why one can, even if this information was not there, one would still be able to guess that this must be a bright field image, because here there is less scattering. All that is most of the intensity still manages to remain in the forward direction, in the zero beam, non-diffracted beam, etc. So we get. So this is understood. Yeah. So how we interpret the contrast in this? Now, one more additional thing. What about this one? Silicon and here. This is most obvious. Let's talk about it. So this is all volume aluminum nitride. Yeah? This contains maybe columnar grains. This let us say is one column, another column. So this is a columnar grains. So this is one grain. This dark definitely must be another grain, and then there is another grain and so on. But it is columnar grain. Now you see this. Here we see contrast, and that contrast is actually due to diffraction contrast, because this particular columnar grain was differently oriented or is differently oriented in comparison to this dark one. Their diffraction conditions are different. This one is not diffracting. In the case of bright field, is not diffracting. Therefore, most of the intensity from this region still manages to remain in the original beam, whereas from this part, let's say, it is satisfying the diffraction condition, so most of the intensity has gone away, and therefore when I make a bright field image with the non-scattered part of the beam, I get a dark image for this corresponding to this area. So in a way, diffraction contrast mechanism is, why the intensity changes is due to diffraction, but the logic is same of forming the image and why the contrast comes. Okay, so I think so we have finished with that mass thickness contrast. So that is done. Now we talk of diffraction contrast, for which we have already introduced also. We have seen one example, but we will try to look at it in more detail. For example, the real image. Why is it that my microscopy, electron microscopy images are able to be so sensitive to these grains? One is oriented like this, another is oriented like this, and I am immediately seeing this in the contrast, in the images. And you know, the grain field between maybe this and this need not be very much, it may be very small. Yeah, usually probably it is not so much. It's maybe 2 degree, 3 degree, etc. But still I am able to see this contrast. Why? Such kind of things I think we will try to understand. And for this, this schematic diagram will be very helpful. And you can also by yourself go through this and already understand it, but I will also take you through. So this is a representative schematic of a crystalline sample, and we have the incident electron beam, and basically a Bragg diffraction law is sort of schematically shown here. And so these are the lattice planes, or these are the lattice planes. Yeah, let's say this is a relevant lattice plane and this is the incident beam, and they have shown that here the diffraction takes place. If the path length between these two rays is a multiple times of lambda, then we get a constructive interference and we get the so this is the path difference, which is equal to CB plus BB, and if that path difference is equal to n times lambda, then we are going to have a constructive interference or diffraction. Now, so this is the equation 2d sin theta is equal to n lambda, and we already referred back to this equation right at the beginning as to why we are using electrons for studying crystalline materials, because crystalline material is like a grating, three-dimensional grating on the atomic scale, and then we use electrons which have got sufficiently lower wavelength, and therefore it works out. That's what we talked about. That fact we will highlight it in a more quantitative manner here. So that there is a Bragg's law is, I think, more or less clear to everybody knows how. And now we just try to analyze that equation in terms of, or with respect to the electrons. That's what we will try to do. Just fit in the values of lambda. As a matter of fact, I think I have tried to do that. So let us assume that the lambda for 200 kV electron beam, which is what it was available in our microscope also, then that would be something like 0.025 angstroms. Yeah, that's the wavelength of, if we put that in, which is here, and just for the sake of simplicity, let us even treat it as 0.02 angstrom. Doesn't make, we just want to understand. And here the interplanar spacing is given as 4 angstrom. make that as, let us say, make that as maybe even 1 angstrom. Yeah, it doesn't matter. So then if you put that, it will become 2 d is 1, that remains 2, and then there is sine theta. 2 sine theta is equal to n into 0.02. Yeah, n is, let us assume n is 1, first order diffraction. So we have 2 into sine theta is equal to 0.02, which means that sine theta has to be, sine theta is how much? Sine theta in that case is 0.0, we said we call it as how much? 0.02 angstrom, isn't it? 0.02 divided by 2. So 0.02 divided by 2 will be 0.01, isn't it? 0.01 is 1 by 100. So sine theta value is 1 by 100. Now at such low sine theta values, if this theta were given in radians, then you know that there is an approximation that sine theta for very low theta is equivalent to tan theta equal to theta. So basically, which means that for typical values of our crystal, typical polycrystalline samples, this theta value is going to be extremely small. So it will be like how much we calculated, 0.01 radians, and if you convert that into degrees, even then it will be of the order of less than, I mean, it will be few milli degrees probably. It will be less than 1 degree, because 57 degrees is 1 radian. So ours has to be much smaller than 1 radian. No, not even 1 radian. It has to be much smaller than 0.01 radian, and therefore this theta value has to be less than a degree. What it means is that our electron microscopy is going to be, we are working, and that this you try to contrast with what is happening in X-ray diffraction. That you do as home exercise, and probably we will do that in the afternoon today when we solve the exercises. We have some exercise which handles this part. So in the normal X-ray diffraction, the angles involved are, if you imagine any X-ray diffractogram, you vary your theta angle to theta angle from 4 degree to about 90 degree, isn't it? Whereas here, everything is happening in less than a 1 degree. Correct? So the angles are extremely small. So the Bragg's law is working on very, there is nothing, we don't even go up above 1 degree, let us say. So everything is happening less than in a 1 degree. And that's where is the uniqueness of electron microscopy or diffraction contrast microscopy for studying the defects. Now why is it that this has any relation to my material? It has relation in the following way, that like in the earlier image I said, there were 2 grains, one was like this, another was like this. Even if they were only slightly tilted from each other, even if that tilt was, let's say, 0.01 degree, my this equation in electron microscopy will get changed in a very drastic manner. Yeah. So even if, and because the angle involved is extremely small, so even if there is slight change from that angle, it's going to be affecting the Bragg diffraction condition in a significant manner. And that is why this electron microscopy is extremely good to image or to study defects. Okay. I think this part is clear, and we now go ahead. So diffraction contrast. Yeah. So in a way, this is what is diffraction contrast in EM images refers to contrast that results from Bragg diffraction at lattice planes. Okay, this is fine, but this will not allow you to study defects. What are defects? Defects are that lattice planes get bent locally, and this bending can be very small. It can be only less than a degree. But my Bragg diffraction is capable to detect that even very small degrees of bending of the lattice planes. This bending happens at close to the dislocations, precipitates, any kind of defects, grain boundaries, etc. This bending will happen, and I have this unique technique of detecting that bending. So that's how the diffraction contrast works. And maybe here are some examples. Thin crystalline foil which is bent produces diffraction contrast because Bragg diffraction changes across the sample. Yeah, I mean Bragg diffraction changes, that's correct. And also my Bragg equation is suitable to detect that change in the Bragg condition, because my Bragg diffraction condition for the electron microscopy deals with angles which are just 1 degree, and therefore any small change in the lattice planes, in the bending of lattice planes will be detected. crystalline precipitates embedded in a crystalline matrix may show different crystal structure or crystal orientation. Yeah, this is not necessarily to do with bending, this is strictly only diffraction. And these locations also produce bending of lattice planes and so on. So we will see each of these. Now here's an example. This is a silicon sample, bright field image of a silicon sample. This silicon sample is, of course, it has to be TM sample, so it has been thin. It was probably particularly thin, and this any sample, if it is made extremely thin, it will tend to bend. That's quite common sense. So it was also bent, and then if we acquire a bright field image, you get an image like this. Now this silicon happens to be actually single crystalline, so it's perfect. No defect should be there, but we are still seeing an image like this. Yeah, so this is strange that when there are no defects, etc., why should there be such an image? That actually this is to do with the bending. Because my sample is not uniform, it has got bend, which can happen to any sample, and therefore, and since it is bent, my Bragg diffraction condition is sensitive to that bending, and that's the result of it. We will see it more detail. And then I have, let us say, I go to slightly thicker area of the sample. That's why it is also slightly darker, as you can see. Yeah. Why? What is one reason why it should be darker? This is also silicon. This is also silicon. Why is this image darker? Assuming that they were both acquired under same acquisition conditions. Why is this image darker? Thickness is better. Now one thing, if it is more thick, then it is less likely to bend. Okay, so bend contours, this is how we have eliminated bend contours. Still I see this some contrast in this image. Why? Again, I have still a perfect crystal. There should be no defects. Why am I seeing these fringes here then? Is there some strange defect which is like in the form of fringe in my material? It cannot be. This would be very strange, isn't it? When I say I don't have any, so there is no defect. In fact, these are called as thickness fringes, and they also occur due to diffraction which is taking place, and we will study that also. Good. Now, when we want to now study these diffraction phenomena which are happening, you might have probably understood if there is a sample, electron beam is falling on it. You have seen in the earlier slides that there is tremendous amount of interaction between that electron beam and the sample. And one reason why that interaction is going to be extremely dominant or quite significant is because charge-charge interaction. Electron beam is also charged particle, and matter also contains a lot of charged particle. Therefore, the interaction is going to be strong in comparison to that of interaction between light and matter. There the interaction is relatively weaker. So inherently we cannot really say that this interaction is going to be handled by let's say single scattering. It might be quite multiple scattering, because the so-called what length it is called, scattering length, collision length or whatever, that is going to be extremely small. So there are this likelihood that it will actually scatter multiply. And then, but just to get an introduction into it, to start to understand the phenomena, we assume so-called kinematical scattering. In the kinematical scattering, following assumption is made that if this is the incident beam, and as it is going on through the material, that there is scattering. Okay, so it gets scattered and like that. But nonetheless, this scattering is weak. This scattering could be weak. I don't mean to say that suddenly the electrons have began to scatter weakly or interact weakly with matter. No, I don't mean to say that. But it could have been weak because of sample being extremely thin. It could have been weak or relatively weak, let me say, because my sample contains light elements, such kind of things. Or just let us make an assumption that the scattering is such that I can assume that even when my beam has passed through the sample, relatively more or less only little amount of scattering has happened, and most of the intensity is still preserved in my outgoing beam. So this, even at the end of the sample, even when in the transmitted beam, here we start with intensity 1, and we still, even after the beam has passed through, I still have the intensity 1. This is of course an artificial assumption, but we make it just to begin to understand, because in physical sciences we always make this. We hypothetically simplify the problem. It's one case of like that. So and then there is scattering. So although this scattering is happening, I still take that the zeroth beam magnitude is still 1 in such kind. There I might have written also that the single scattering and that the loss of electrons that is happening here, that we neglect. So under these conditions, it is possible to derive a formula for the scattered intensity. Yeah? So for this scattered intensity, it is possible for this scattered, this is magnitude, and then square of that would have been intensity, and the formula for that intensity is this one. So this F is structure factor, this must be volume of the unit cell, and so on. And this is, so let us understand what are the various parameters. This I told is a structure factor, which in principle you should have heard in the previous 2 lectures, isn't it? How to, you have probably calculated structure factor for FCC, this, FCC at least you have, and in great detail. This is the unit cell volume, and this is sine square. Pi, T is the thickness of the sample, and S is the excitation error, and that denotes how far you are away from the Bragg diffraction condition, and this is pi s g, like that. So this formula has been derived, and this is called kinematical theory. And yeah, now it starts to get little, we are of course going to a little later, we are going to modify this. We will have to bring in dynamical scattering effects, but let us first begin with the simple thing. And so I think I will not be able to tell you how this was derived, but to some extent you must have learned it in the previous 2 lectures, at least partially. Now we try to understand this equation. Okay, so I was also told that most of you have understood this Ewald construction and all that. So here is what is Ewald construction. This is the incident wave vector k0, and we have drawn a sphere. Yeah, and this Ewald, this wave vector is terminating on the origin of the reciprocal lattice, and once in this way we have fixed this incident wave vector, and around this wave vector we draw a sphere, and that's our Ewald sphere. Then we have a reciprocal lattice whose origin is here. Yeah, so this completes the picture. And then I hope you might have also learned about railrods. Yeah, so the reciprocal lattice points are ideal points only for a crystal which is 3-dimensionally infinite. The moment you make it finite, it's going to go the reciprocal. So this real lattice and reciprocal lattice you must have spoken of in great detail, even with formulas. That if I have a real lattice, by itself, by its very definition, it means that it is infinite, and that these lattice points are of course small, but it is infinite. This crystal is infinite in size. And if I now make a corresponding reciprocal lattice of that, then I get again lattice points which are, let's say, point objects. But if this crystal lattice becomes finite, that is, its dimensions begin to shrink, then the reciprocal lattice points are no more ideal point objects, but they begin to increase in size. Now here is an assumption, or let's say, and typically, yeah, here it is drawn, this is my sample. In this case, we make our sample thin in one direction for the electron beam to pass through. So if I start to go away from that ideal condition of a lattice in the z direction, then of course my reciprocal lattice points are also going to increase in that direction. Correct? So in this direction, in the real lattice, if I decrease, then in the same direction in the reciprocal lattice I have to increase. So that's why this reciprocal, instead of having points, I get rods. Okay, so this was also probably conveyed in some way. And now I have this Bragg Ewalds, and this Ewald sphere, we know that the Bragg diffraction condition is wherever this, if this Ewald sphere cuts a reciprocal lattice point, then it is that particular reciprocal lattice point satisfies the Bragg diffraction condition. In this case, it doesn't even have to be a lattice point. Even if it cuts the rail rod, you are going to get some intensity in the diffracted beam. So that has been now I hope this much is clear. I mean, this is even solid state physics, basic. You will find it probably in any solid state physics book. Ewald's construction and that what is the Bragg diffraction condition, and even from looking at from this point of view is also there. What is probably not so clear is even when this Bragg diffraction condition is not satisfied, even then we get diffraction. And why we get it is because of this relaxation of Bragg diffraction condition. Yeah? Okay, good. Now this point is going to be relevant to understand our further images. So you please pay attention. So let us consider the case which has been given here. So let's say this is the origin of the reciprocal lattice, and this is the first, or this is another reciprocal lattice point, which is of course different from origin. And this is my Ewald sphere. And in this particular scenario, this particular rail rod is being hit, is being cut. So some diffraction will take place. Okay. But from the ideal diffraction condition, I am off by this much distance. This is denoted by S. Okay. Now suppose I change my, either I change my incident beam or I change my reciprocal lattice. You can do it both ways. We will probably think as if that, let's see, we will assume that we are changing the Ewald sphere itself, the orientation. So instead of like this, so right now this is the magnitude of S. So let's call that this magnitude of S is maybe 2, just for the sake of just some idea, some number. Now I tilt it in such a way, so instead of having it like this, I make it something like this. Then this sphere, Ewald sphere, will come closer to this reciprocal lattice point, and it will maybe, let us assume that it hits it exactly. Now there is S is equal to 0. So in the second case, the latter case, it exactly satisfies the Bragg diffraction condition. And then of course when it exactly satisfies Bragg diffraction condition, there is going to be more intensity. And how can we understand that there will be more intensity? If you look at this equation, if we substitute that there is this S is equal to 0, or it tends to be 0, then you see this S becomes 0, and you can do some trick wherein you put here T and here again T square. So this you can do it, isn't it? So I just put here T square and T square. I divide and multiply by this as T square, and this pi T S G I give it number theta, let us say, I call it theta. Yeah, so limit theta tending to 0, sine square theta by theta square, that becomes 1, because limit of sine theta by theta is, when theta tending to 0 is 1. But when that is the case, but this term, now this is a non-vanishing term which is 1, and so I have this term which gives the intensity. So I have maximum. And if you plot this function as a function of let us say yes, this is what you will get. Yeah. So at S is equal to 0, I get maximum intensity, and as I go away from S, the intensity decreases. But there are also additional secondary fringes, which means that for this particular S, you again get a secondary maxima and so on. Okay. So this much is clear. Yeah. Now the message to be taken from this is that depending upon how I am oriented, how far I am from Bragg diffraction condition, I will get this particular intensity in my diffracted beam. And this is like a sinusoidal function, isn't it? So that was with respect to yes, that is this how far I am from the Bragg diffraction condition, or in a way how is my lattice plane bent. Yeah. So if these two are related, but you will see that apart from this yes parameter, there is and so I told that yes is, which is related to how far I am from Bragg diffraction condition, is related to bending. And because of this, suppose I have a plane sample and somehow I thinned it, and because I thinned it, it got bent. So locally it is bent everywhere, yeah? Somewhere more, somewhere less, etc. And I have put this sample under the electron beam, and this is the equation which is going to play out in getting the diffracted beam intensity. So depending upon how that S parameter is, I will get everywhere different intensities. Yeah. So although my sample contained no defects, it was actually uniform defect-free sample, but it was made thin, which I usually do when I prepare a TM sample. And because I made it thin, it got bent locally, and because of that local bending, this equation played out that the intensity is varied locally. And this contrast is bending contours. Bending contours, yeah, it's called bending contours. We will see how they look like and all that. That's one thing. But let us assume that somehow I have found one material which even after making thin doesn't become bent. Okay, so the bending contour is ruled out. And let us assume that I have explained how to prepare TM samples in a conventional manner, in which case we always end up getting a wedge shaped sample. So it is when we have that sample, we create a hole in the center using ion beam. So at the boundary of the hole, it is very thin. But as we go away, then it starts to become thicker and thicker. So effectively, we get a wedge which is circularly symmetric. Now I have such a sample, I have put it inside the microscope and I make an assumption that there is no bending, it's stable, it's not bending, but there is thickness variation. And this thickness variation is of course also going to play a role, because you see there is a parameter T also here. Because, and in a way you see T and S, they are more or less symmetric. I mean, the manner in which yes, this function is dependent on yes, in the same manner it is dependent on T. Okay, so that's why it is going to show periodicity. This sine function is there, so there will be periodicity. So in the same manner, as T increases, you are going to get similar thing, and that will be thickness. So those are the two factors which we saw. So this was the bend contour, and this was the thickness fringes. Thickness fringes look fairly, I mean, they look as if they are regularly arranged, because the thickness, as I told, will more or less regularly increase as we go away from the hole of the sample, whereas the bending can be very haphazard. You can't say that it will bend this way or that way. That's why this looks very haphazard, whereas here this is the hole, and as we go away from the sample, thickness increases, and then you see that as thickness increases, the fringes are appearing black, white, black, like that. Whereas bending is more random, and therefore the contrast is also random. Okay, so this much is, I think, also fairly clear. This we have discussed. Yeah. Now we will continue to discuss that equation by and large, but we will now tell as to the inadequacy of that particular equation, because that was this equation. This is another way of writing the same thing, but in a slightly different way. Earlier we were using this tau is, I believe, thickness, or a parameter which is related to thickness, and omega or W is a parameter which is related to S. Yeah? So don't worry about it. We are anyway interested only in the qualitative analysis. If we understand the crux of it, mathematics you can work out yourself, doesn't matter. So that's how it is. Yeah, and we will see that this equation as it is actually not very correct. Why it is not correct, we will see. Because that equation, if you plot, there are two parameters T and omega, so or tau, which is like it has been, how do they say, it has been parameterized. That's the word. So this is tau, which is related to thickness. This is W, which is related to SG. That is the excitation error. But with this we have no problem, isn't it? And this is the equation, and this equation is used to make this plot. What is plotted is, this is like a two-dimensional plot. On this axis is thickness, on this axis is, shall I always call it excitation error? Yeah, how far we are from Bragg diffraction condition. I will keep calling it as excitation error. Is that okay? So excitation error on this side and thickness on this side. In a way, this is related to bending of the sample, this is related to thickness of the sample. This is also clear. So and this is an analytical function, and I can always plot it, a two-dimensional plot like this. Yeah, you can maybe use any software, MATLAB or whatever you must do, and can be plotted. And when we do that, we are going to get the intensity as a function of these two parameters. And if you see, let us look at now the inadequacies of what all, or let's say inadequacies of this equation derived by kinematical theory or kinematical scattering assumption. Here it is 0. This omega is related to a Bragg diffraction condition, and so I am satisfying the Bragg diffraction condition exactly fine. And here its thickness is increasing. So if I go along this axis here or this line here at Bragg diffraction condition, and what is it's all right. I am going in this direction means I am increasing thickness. And you see what will happen if I make omega as equal to 0, and I keep on increasing the thickness, how will this function look like? Any guess? What will happen if I make excitation error at 0? Yeah, just let's make excitation error at 0. Can anybody quickly point out what will be the outcome of this when omega is made, when W is made to 0? Yeah, the same logic. Okay, same logic. Okay, which means that we have to maybe just we make it like we multiply and divide by pi square t square. So here we have pi square t square, and this parameter the limit goes to 1. But I have this pi square t square. Remember what is there? Pi square t square. Now if I increase the thickness, of my sample, that's what we do when we go along this axis. What is happening to the diffracted intensity? Diffracted intensity is increasing. Yeah, and there is no end to it. It will keep on increasing. This is very artificial, isn't it? Which means that I have a TM sample and there is a hole inside it. Yeah. So at the hole of the sample it is thin. As I go away, it starts to become thick. Yeah. But my equation is telling me that, and I make, let us say, a dark field image of it, and it is saying that you will keep on getting intensity in the dark field image. This is very unrealistic, very unpractical, isn't it? So that's why there is a problem. What is another problem? Another problem, let's try to look for another problem. Okay, so we are considering the case along this dark line. That dark line corresponds to a situation wherein my sample satisfies the Bragg diffraction condition exactly, and we are looking at the influence of increasing the thickness under such conditions, that is exact Bragg diffraction condition, and this is going to expose the is the problem with the kinematical theory. What happens is when we make excitation error equal to 0, then this becomes this, and which means that this equation tells, or this plot which is plotted here along this line, this equation is precisely plotted along this line. It says that as we increase the thickness, intensity in my diffracted beam will keep on increasing. But this is not realistic. This is not what really happens, and therefore our kinematical assumption fails. Our kinematical scattering assumption fails. Yeah, so that's one thing. But does it hold good anywhere? It does. It does good. But that probably we will speak a little later, or maybe little later. Let's look at. So this is clear now. Yeah. Now let's look at, is there any other problem? One, it was said increasing sample thickness. This we have clarified. Bend controls. Okay. Okay. From this equation alone, probably it will not become clear, but in the next slide there will be an opportunity wherein we will see the second case where it fails. And that second case is going to be for a line which is like this. Yeah? And so, but before we explicitly look at that, see how will the plot of, now let us assume that, yeah, in a way, okay, but wait a minute. So this case we have considered. Let us case like this is a thickness variation case at Bragg diffraction condition, at exact Bragg diffraction condition. Let's look at thickness variation at when we are away from Bragg diffraction condition. That is denoted by here, this white line. And there we see that things are not so bad. I mean, at least it makes some sense, because we are here, and for that probably this analytical function will not boil down to some simple equation like this. So we will have to plot, and that's why it has been plotted. And we have to now make our analysis or interpretation by traveling literally along this line, and we see that as we go, when S is not equal to 0, and as we increase the thickness, we will see that our intensity will, here for example, more, dark, again bright, dark, bright, dark, bright, dark, like that. So we get fringes, and that's thickness fringes. This is what we also observe. Yeah. So this makes more sense, correct? So it fails when S is equal to 0, but when S is not equal to 0, is away from 0, then it is able to tell us at least qualitatively the way we observe things in our images, like we observed here. That as the thickness increases, there is dark, bright fringe pattern is there, and that's what we see. Yeah, but okay. So that we have seen, and yeah, now these two cases we have seen, and we will now talk about the other case. Here we keep the thickness. See, here we keep the thickness constant, but we change how far the sample is bent. So at this point, there is no. It is satisfying the Bragg diffraction condition perfectly, and there it shows maximum intensity. As we go away from it, it shows less maximum, or the intensity decreases, but there is still fringe pattern. I mean, there are secondary maxima there also. So we again get a fringe pattern, etc. So this is what. Now we probably go to next slide, which will be example of this case. Yeah. So what all I told is sort of displayed here. This is some kind of bent crystal. Incident beam is falling in this direction, and let us say this. Yeah. I mean, here as you can see, the lattice plane here is like this, whereas lattice plane at this point has been bent. It is like this. Here it is in the other direction, and the incident beam is a parallel incident beam which has a fixed direction like this. Now let us make an assumption that at this particular point, the Bragg diffraction condition is exactly satisfied, and which means that corresponding to these lattice planes, you get a maxima here, and this is the same function which we have so far been knowing of, that kinematically derived equation, and this has been plotted here. And this same intensity, so this is the intensity in the diffracted beam, and here is a dark field image, and as you know, dark field images are made with diffracted beams, right? So here is this is some silicon sample, and they have used the 400 diffracted beam to make an image, and this is plotted here, and you might be able to see it much better than I do, that this is the central maxima, but there are also side maxima are also there, and though when you plot it, it shows like this. This is an experimental curve, and this particular is a calculation from that equation, and they match reasonably. I mean, at least you see that, okay, I mean, I am at least able to understand this behavior here. So now now what can we say about this from this image is that this particular area here along this line is where S is equal to 0, and as I go away from this to this side and to this side, I keep on going away from the Bragg diffraction condition, and is schematically displayed here. Along this line, yeah, I have Bragg diffraction condition exactly satisfied. As I go away, the Bragg diffraction condition, I am going away and away from Bragg diffraction condition. But I am able to at least make some sense. But this holds good when the sample is thin. If the sample becomes thick, then this doesn't hold. It doesn't hold good in experiment. Here, according to this equation, which according to our kinematical equation, it holds good at all thicknesses. This is what it will show, isn't it? Here it will not, because you look at this equation, this plot here. It says that irrespective of any thickness, I have drawn this curve or this line here. Even if I draw it here, the pattern is likely to be similar. Maximum intensity when Bragg diffraction condition, and as you go away from the Bragg diffraction condition, it is going to decrease, but also going to show side fringes. But this is not really, and that's so. When the sample is thin, this holds good, as we have seen in the experimental thing, because this plot we can make anyway. I mean, we made the assumption, derived the equation, made the plot. This is super fine, but it has value only when it matches with what we observe in the image. And here it is matching, but there are places where it won't match. And this is the example. This is the case where it is matching thin area of the sample. This is the case where it is thicker area of the sample. And here the same thing is drawn. 400 dark field image. I mean, the dark field image with the 400 reflection. and here also 400 image with a 400 reflection, but what do you see here? And yeah, it's not probably the same area, it's different area, but here we see that in the center there is a dark field. There is a dark, there is no maxima there, there is a minima. So that's the problem. Okay, now we try to understand, that is, these are experimental, so these are more valuable. This is what we is the final thing. So here, thin sample, kinematical theory works. So these are called rocking curves. Somewhere word is there, or bend contours, whatever, it doesn't matter. So yeah, so this equation holds good here. This equation derived kinematically scattering, considering kinematical scattering, doesn't hold good here. Can we make things better? But before we go to that, these are two dark field images. This is one dark field image, this is another dark field image at a thicker area. These also you will observe, but you don't always make dark field image, and you are also probably will be familiar with these kinds of images, because we mostly stay dark field image. Only at very few occasions when we have a deliberate intention, we make a dark field image. But a bright field image, more or less, we are always in bright field image, and therefore in a bright field image from a thin area you get this kind of structures, and these are actually the bend contours at thin regions of the sample, and there you can more or less, but this is bright field, it's not dark field, yeah, so you have to make that understanding. And therefore here in the earlier case, in the dark field, let us say I had produced, in the dark field you will never be able to see the complete area. Okay, let me make that point also clear. And what? Yeah. So here, for example, when I make a dark field, one more. When I make a dark field image using this G reflection, only that area of the sample will be visible where that Bragg diffraction condition is satisfied. No other area will be seen, isn't it? That makes sense. Okay. That's why your image will really, you will not even able to recognize what my sample is. You will not feel like I am looking at my sample. It is by and large hidden. It is dark. Only few, because there is no other contrast. The only contrast is this one. So you will just see a line like this. I mean, if I say this is the image of my sample, you don't even know where the hole is, where the sample is beginning, where it is. So for, and therefore.
So in the literatures of most of the cases go by the bright field has less information compared to the dark field. Usually it has much more information than bright field.
It is correct in the following way, that I am also telling the same. Okay, I am telling slightly different, true, but I will explain. See, now I have this image. This is a bright field image. I feel like I am looking at sample, yeah, from common sense, etc. I can probably understand that this is thin region, is the hole, or whatever. But the information which is here is very difficult to interpret. That's the problem. And I can tell you easily why, for example, is that the case. When I have this image, I know I have acquired this image with 400 reflection. I know only those regions are bright where these 400 lattice planes are satisfying the Bragg diffraction condition. So I have this additional information that in this part of my sample, the 400 lattice planes are satisfying the Bragg diffraction condition. This is the information which I get additionally. When I have a parallel beam, when I have a bright field image, in this, it's all mixed up. You can't make such a conclusion that along this line, it is what I see is satisfying this condition or that condition is difficult to make. So from that point of view, dark field image is more informative. Okay. Yeah. So in this case, it's a thin sample, and then you can, for a thin sample, it is possible to apply that equation, and you can get the size ranges, etc. And that can be done. I think we are going very slow. I am going into too much detail, but let us slowly make things fast, because I think I have basically explained all the crux of the whole thing in a great detail. That was thin area of the sample. This is thick area of the sample. Yeah. The aim of showing this is, apart from the fact that I mean the dark field image looked as if you didn't know where the sample existed even physically, etc. When you make a bright field image, it looks like this. In thin region, it is like this, and you can say these are the bend contours, and you may even interpret it and like that. But when you go to thicker area of the sample, things get even more complicated. That you get your bend contours start to look like this. Now it is not anymore possible to say I have this bright fringe, or in the bright field case dark fringe surrounded by side fringes, etc. Because here it was fairly clear. See, yeah, this must be my bend contour, and that here there is a secondary dark fringe. On the other side also there must be a secondary dark fringe. Then this is a bend contour which corresponds to another reflection, or in this area I have one bend contour, I have another bend contour, and that for this bend contour here is the side fringe. For this bend contour here is the side fringe and all that. So this was fairly easy to interpret and understand. And I can even say that how should, so I can say that along, so I can imagine if these are, for example, so I can say that along this line, it is as if I am exactly in the middle of the Bragg diffraction condition. Along this region, Bragg diffraction condition is satisfied. Along this line, Bragg diffraction condition is satisfied. I'll just try to interpret, explain you. See, I have a sample which has been bent slightly like this, and there are lattice planes. The schematic diagram which is shown here. It is shown here in a upward direction. Doesn't matter. Suppose this is my incident beam, and here it doesn't satisfy the Bragg diffraction condition. In the sense that suppose Bragg diffraction condition is 2 degrees. Just make an assumption that in my Bragg diffraction equation, the angle of satisfying the correct Bragg diffraction condition is 2 degrees, and here it is, for example, 1 degree. Yeah, here 1 degree, and the incident beam is there, like this. But my sample is bent. Now here it doesn't satisfy Bragg diffraction condition, but here these planes they bend like this. So here the angle between incident beam and lattice planes is 1 degree. Here it will be exactly, it will be 2 degrees here. Similarly, from the other side also it will become, because it will bend in the other way. So these two regions are satisfying Bragg diffraction condition. Here it is not, it is away from Bragg diffraction. That information I can draw from this, that my sample is bent in such a way like this, that here and here it is satisfying the Bragg diffraction condition, here it is not satisfying. But when I make this, when I take the same sample in thicker area like this, becomes very complicated. Now it is difficult for me to really draw any analysis, isn't it? This is because my sample has become thick. Those nice fringe pattern, individual fringe pattern which was coming is now no more the case. So many effects are overlapping with each other, and that's why these strong dynamical diffraction effects are coming up. I mean, it need not even be so that like here earlier where it was where there is a dark maxima, or let's say dark valley. We saw that in the dynamical effects that need not hold good if the sample is very thick. There might be a bright maxima also when you make things. So it's difficult to interpret. That's why this image was shown, and it's a good point to try to consider dynamical effects. So people have tried to consider, okay, we try not to neglect the diffracted beam, and so therefore they have, how do they consider it? Now mathematics becomes slightly more complicated, so I have tried to show it here. See, this is the diffracted beam intensity, this is the zeroth beam intensity, and now we don't anymore say that the zeroth beam intensity is going to remain constant, that is one. We take away that assumption, we don't make that assumption anymore. In a way, actually this is written as a sort of I think this is written in a matrix form, isn't it? So, but what this shows is that the rate of change of diffracted beam intensity is dependent upon not only my diffracted beam, let's say the diffracted beam intensity at that point, but is also dependent upon what the zeroth beam intensity was at that point, which means that this is shown by this kind of thing. So there is some what it is called back reflection, that is incident beam is scattered into diffracted beam, But in the dynamical thing, it is also possible that this diffracted beam can again backscatter. So we have to now consider that. So that's being solved by these two differential equations. So basically the meaning of this equation is that if I consider the diffracted beam, I have, using this parameter, there is dependence on the diffracted beam intensity at that point. But using this parameter, it is also dependent upon the incident beam or the zeroth beam intensity. Same holds good for the non-diffracted beam or non-scattered beam. It depends, using this parameter, not only on the how does it work? Yes. With this parameter, not only on the zeroth beam intensity, but using this parameter, it also depends on the diffracted beam intensity. So that's the meaning of that. One practical example of this is so-called, this is called as a double pendulum, is it? Yeah. So there are two pendulums and there is some link between them, some interaction between them. It's exactly like our thing also. So if we make a kinematical assumption that there is no, then if we keep this, if we move this, then this will remain stationary. But under dynamical considerations, when we make this through this interaction, slowly the vibrations will be transferred from this to this. This will at one point of time even become stationary and only this will be moving. After again some time, then it will again transfer back the energy back to the first one and so on. So our thickness fringes and all these dynamical effects which we are seeing are actually like this. Now when this equation is solved, we get something like this. Now it actually looks quite similar to that of the earlier one. Only that instead of S, we have now S effective. What is S effective? S effective is written like this. And it is actually quite related to normal S. Only that something has been added to it. And okay. So how is it that whatever this new form of S, which we are calling S effective, how is it going to solve our problems? If you think, it does solve our problems. Where was our first problem? Our first problem was when S was 0, then we were taking that limit and things were getting complicated. Now, are we entitled to take that limit? Now not anymore, because here you see S effective is equal to this S square plus 1 under root divided by epsilon g, or how is it this called? Zeta g. So now even if you make S is equal to 0, S effective doesn't become 0. So that limit tending to 0, which was causing us problem, that doesn't happen anymore. So it is this way that this helps to take care of things. And so, but as I said, yeah, I'm going in between. I mean, sometimes I'm using S effective, sometimes I'm using W, but don't worry, I mean, these are just parameterizations. So here it is written in this way. Now when we go from kinematical to dynamic, this W is replaced in this way. Yeah? And the same logic. Here, when I make W is equal to 0, I end up into problems. This case here. But here, when I make W is equal to 0, let's say old W equal to 0, the dynamical W doesn't go to 0. And that solves some of our problems. And that's how, when I make a plot, then I get this kind of, this is the realization of this equation or plot of this equation, and this is more close to reality. And there should be examples. I can show you also experimental images which look like this. In fact, I acquired them myself also, very easy. Had there been samples, we could have even tried to even show this on microscopy, but may have worked out, may not have, it requires some time, but doesn't matter. So now, using that modified equation, when from a thicker area, this is the experimental plot, this is the theoretical plot of the modified equation, and we can see that we are able to now, this is the experimental intensity profile, this is the theoretical profile using that equation, and they do much better. So that's done. This was for the bend contours. And then, and thickness fringes, I think we have spoken of quite briefly. And so how that, I have, I think, spoken of that there is a periodicity dependent also on T also, and therefore we get thickness fringes. Here actually we have a wedge-shaped sample. So the thickness, when we look at the image, they appear as if here I have one fringe, here I have one fringe, here I have one fringe. But that has not to do with our lateral variation. It has to do with the fact that here the thickness is different, here the thickness is different, and so on. They appear to us in the image that as I go away from the hole, I get fringes. That is in the image, but the background for that is that the thickness, as we go deeper inside the sample, changes. So, but that I think you have understood. So, and the example of that is here. Yeah. So this is again silicon, and we see that here are the fringes, and these fringes here the S is equal to 0. Yeah. Ideally, yeah, even for thickness fringes, for example, that S is equal to 0 would have failed, because at S is equal to 0 we should not have got any fringes. But we do get fringes. Here is a perfect S parameter has been, because that Fuji line is going exactly through this one. So there is a but we see fringes. But now with dynamical theory, we can still explain those fringes. And for when S is equal to small, then we get the fringes, but the spacing between the fringes has changed. If we make even worse, then the fringes become even smaller. Yeah? And all these effects can be explained by using, in fact, that the spacing changes can be understood even by kinematical theory also. But this would not have been possible to be understood with kinematical theory. This would have required that. Maybe let me go back and a little bit more explain this equation. So this was our kinematical thing, this was a dynamical thing. Now even by looking at it, we said that kinematical was doing fine when we were not close to S is equal to 0. That's what we said also, isn't it? So you see, you just compare the two and you will again make same inferences. Look at this part. Look at, maybe we said that when we go away from S is equal to 0, we are still fine with kinematical theory. And if you see, if you avoid probably this particular region here, this part here looks fairly similar, isn't it, in both treatments. Similarly, when we are at thin regions, let's say in this part here, this part for both dynamical as well as kinematical again looks similar. So it is also possible to draw many inferences just keeping in mind the kinematical theory also. So it just gives us confidence that things are not as bad as, but one should keep in mind that there are dynamical effects also, and that they might have to be taken into consideration. So I think that we are probably done with mathematics, I think. So we have understood, we know enough to start quickly interpreting the images. So now these are nanoparticles, and they are of this kind of shape. And as you can see, this is indeed will have, this is prone to giving thickness fringes, because now this is like a wedge-shaped sample. This is a nanoparticle, but still it is wedge-shaped. And for example, this one, looking from the top, this may give thickness fringes like this, and so on. There might be many other examples if you can search and identify. So these were nanoparticles synthesized by Professor Benjamin and his colleagues, and that they have seen this phenomena of thickness fringes using TM, and they probably interpreted it according to this. Or probably, in fact, I believe that they got these images and they must have inferred this shape in a backward manner. So this is how it helps. In a way, it's good. Why? Where is the use of thickness fringes? So I think this is the use of thickness fringes. Yeah, good to know that we can look at it from this angle also. So that's nice. So this is a routine example, let's say, and we have here a case where this is the matrix and this is some precipitates or like that, and this is a practical example of it. This is a bright field image, and what has been done is that this is a sample wherein only precipitates were oriented in Bragg diffraction condition. In metallurgy, it might be possible I mean, metallurgist of you, amongst you might be able to synthesize a material wherein all the nanoparticles or precipitates are probably crystallographically oriented in one particular way. Yeah? Whereas the matrix is probably something oriented in another way. So you can then orient your sample in such a way that only the precipitates satisfy the Bragg diffraction condition and the matrix doesn't. In that case, you will get, and now this is a bright field image, and you will see that it will so happen that since only the precipitates satisfy the Bragg diffraction condition, intensity is scattered away from the 0th beam, and if you now make an image with 0th beam, it's only the precipitates which are scattering away the intensity will look dark. They all look dark, for example. But this holds good only if that metallurgist is able to synthesize his material wherein all the precipitates, they are oriented in the same way. Okay, so that is a must. This may not always be possible. In fact, if you just prepare randomly a sample where the precipitates are there, most of the times precipitates need not be always oriented in a particular direction, all in the same direction. In that case, of course, things will be different. Those which satisfy the Bragg diffraction condition will look dark, but those which don't need not look dark. And here, of course, it's just a complementary thing. Earlier it was bright field image, now it is dark field image. Dark field image we make with the diffracted beam. There, all these precipitates are getting scattered in the diffracted beam, and therefore they all look bright in the dark field. This is, I think, clear. The schematic of that is shown here. Good. Now, here is another example where is lead selenide quantum dots on carbon foil, and here we see both effects, mass thickness contrast as well as diffraction contrast. Why mass thickness contrast? Because all these nanoparticles, quantum dots actually, they all are looking dark. This is a bright field image. They all look darker in comparison to that of the carbon film which is below them. This is directly a consequence of the fact that at this particular, any region, let's say even this is probably looking the faintest of it, this faint is still more bright than that of the, less bright than that of the region between the two particles when there was only carbon film. So it's directly a consequence of mass thickness. But among the quantum dots, some are looking more dark than the others. That is the consequence, because those which are looking dark are diffracting away more. That's the contribution or consequence of diffraction. So I think with this mass thickness and diffraction contrast is finished, and we now go to moire fringes. You see, suppose there is a precipitates and there's a matrix, and so this also scatters. It gives rise to diffracted beam of its own. This one, but this diffracted beam from the precipitate and the usual beam from the matrix, they can also interfere. And you have seen probably if you take two patterns, one transparency slide you take and print one pattern, you take a second transparency slide, and for the time being you can assume that their spacings of these patterns, let them be identical also, no problem. And if you now orient them with one another a little bit, I mean, you keep them parallel, then of course they are identical. But you just rotate them with one another, and you will see patterns develop. This is, I think you must have done it at some point of time, or even if you imagine it, you will find that some very long distance fringes will develop, and those fringes, spacing between them will change depending upon how much orientation angle is there, etc. That's one possibility, which is dependent upon the orientation between the two identical patterns. Another probability is that you let, even if they are parallel, but if the spacing in the patterns is different, then again you will see some fringes with longer periodicity. And such kind of phenomena are called as moire fringes. And one example of that is, this is a gallium phosphide matrix, and this is a precipitate. And then I don't know the detailed analysis of it, but these are the moire fringes, because this is 220 nanometers. This is not a high resolution image. It cannot be. It's not a lattice plane image. Okay. So this is that's why I was using the term long periodicity fringes. So but what is behind this is that there is let's say interference between diffraction vector due to matrix and diffraction or diffracted beam due to precipitate.
how G vector indexed over here?
How G vector is indexed? Here, yeah. Okay. So what you were also asking as to why it is, let us say how, more than how, let's first ask why. Why is this indexed here at G? Because this particular image, this is definitely a dark field image. It has to be a dark field image, I believe, or no, not necessarily. But anyway, what was done, definitely it is probably not possible to say whether it was bright field or dark field, but in any case, this particular reflection, one thing, I don't know whether I have opportunity to explain this later or not, but I'll tell you at this occasion. You have in the diffraction lecture, you have heard that we get zone axis pattern, we get two beam diffraction, wherein only two spots are excited, etc. as we go away from the zone axis. Now, this definitely is a case in which it is a two beam condition. Two beam, yeah. I also promised right at the beginning that we will try to relate all the images to the diffraction conditions under which they were acquired. Now, this is an opportunity to do that. And here it is mentioned like this because this image was acquired, whether it is bright field or dark field, but it was acquired, it's bright field. It was acquired with when under two beam conditions, or at least it should have been acquired under two beam conditions, wherein this G220, that is 220 reflection, was strongly excited apart from the zero reflection. Now, why is this done? And this comes to your point that when we do this, we know that all the contrast that we are seeing in the image is coming from the 220 lattice planes, because those are the ones which are only primarily diffracting. All others are not contributing to the image. All the intensity variation that I see is due to the 220 lattice plane which is contributing. And that makes my life easier in interpreting, in a deeper interpretation of the details that I see. This will become even more relevant when we later look at the dislocations. When we try to find out the Burgers vectors of the dislocations, etc., this fact becomes even more important. So now, sometimes there are these are some inclusions in the sampling. This is how we say, or press. Okay, so anyway, quantum dots. Okay. So for example, suppose we have some kind of quantum dots here. This is schematic diagram, and then there is, let us say, there is local strain which has been developed. So, or there are precipitates due to some reason. There are precipitates, for example, and then because the precipitate is there, it's a kind of a defect. So there will be strain around it. And let's assume that this is the strain which is common. I mean, it's the same case. The only difference between the two is here there is inclined illumination, here there is spherical illumination, and let's see how this precipitate is going to look like, or its strain field is going to look like in the image. When I have inclined illumination, then all that what we studied so far for the I mean all these diffraction contrast, Bragg diffraction, satisfying the Bragg diffraction, going away from the Bragg diffraction, all that knowledge you have to now apply here. So bend contours and so on. So here you see, you look at this particular area, and let's assume that here it is an inclined illumination. It's not symmetric illumination like this. And suppose this inclined illumination has been deliberately so inclined that this part of the sample, or in the vicinity of this quantum dot, this part of the strain field which is given here satisfies the Bragg diffraction condition. Yeah? Then this particular part will scatter the intensity, and therefore it will look bright. Yeah? No other part, unfortunately or whatever, no other part is able to satisfy the Bragg diffraction condition. Whereas on the other side, if it is symmetrical like this, then this part also satisfies the Bragg diffraction condition. But if this does, because of symmetry, the other one also has to do. And then in that case, you will get a contrast or image in the contrast in the image which is symmetric like this. So when you make images and you have such kind of structures, let us say quantum dots in your sample, which is creating a strain field, which invariably will then depending upon your inclination, you will get either this symmetrical beam contrast, it is called symmetrical beam type contrast or asymmetrical contrast, and this you can interpret it by using knowledge like this. I think there are some examples. So here the Bragg diffraction condition was such that you had a symmetrical, the beam in this particular area, the beam is falling whole throughout the sample. Is also a good example. At the very first I was trying to explain mass thickness contrast, isn't it? So it's a good opportunity. At this place, everywhere the electron beam is falling. At this particular place, the electron beam, because the sample, this particular area is so oriented that it is turning out to be a symmetrical illumination. In this case it is asymmetric, in this case also it is asymmetric, which means that this sample is somewhere bent like this. Here it is symmetric, and you see here we have symmetrical contrast, here we have asymmetric contrast. Quantitative also you can, when you do calculations you can do quantitative, but I think the slide might be there. This is where it is quantitative property. You have to do calculations about which I don't know much, but this is from a book and example is there. People do calculate. I mean, then you have to again make assumptions, parameterize, this must be that, match it with the observed images, and then you can make more quantitative inferences. And there is also mentioned about semi-coherent precipitates and coherent precipitates. I don't know the difference, but that's so far also. Unless you tell, we will just stick to it. It's alright. So we have understood quite a bit of it. So that's so far alright. And yeah, here is again, I was not knowing whether I will get an opportunity to talk about two beam conditions or not. Then this is many beam zone axis pattern or many beam pattern. This is two beam pattern. We always try, and unless it is otherwise necessary, we always try to acquire images under two beam conditions, because here, assuming that this is the zeroth reflection, only this particular reflection is strongly excited, all others can be neglected more or less, and that allows me to interpret all my contrast in terms of only these particular lattice planes corresponding to that G reflection. And okay, so I would now like to switch to another presentation, because these were slides from Benjamin, with which I am was familiar, but after this he is talking more about his own research, and that I am not so much familiar, so I will go back to for the remaining few slides. So if you give me 15 minutes, I think I will finish it. So let's continue with that and get done with it. Yeah, somebody was asking regarding these calculations and all that. So you see, you have to make such calculations wherein this strain field or displacement field of the defects or around the defects has also to be inserted into those Hovi-Whelan equations or partial differential equations, and this can be solved analytically only in some definite number of cases. In other cases, you have to do numerical calculations and get those kinds of images that we just saw from that book, which were there. But that is okay. Now, regarding dislocations, let us say, how do we measure dislocations? And again, just as we applied this technique for this strain field around the quantum dots, in the same way, similar principles you have to apply. Suppose this is a dislocation. So here, for example, this is a edge dislocation. A lattice plane has been inserted halfway through in your sample, and from the other side this way, and then you see how these lattice planes, they get bent around that core of the dislocation, and then you have to see where it satisfies the Bragg diffraction condition, and depending upon that depending upon, yeah, here there is a trick that, for example, if on an overall structure, for example, I am away from diffraction condition, yeah, and which means that except around this one and around this part, everywhere else I am away from diffraction condition because everything else is more or less same. But around this part, there is chance that I can get back locally into Bragg diffraction condition. Now that may also happen either on this side or on this side, depending upon how everything is formed. So if you follow exactly how it is happening, then either you get contrast from this part of the dislocation or this part of the core of the dislocation, this here and here, or you get it from inside and inside. So that is depending upon whether you are S for the general bigger sample, whether it was greater than 0 or less than 0. So in one case you get the contrast which is inside, in the other case you get it outside. So the same object, same dislocation structure, depending upon whether your S was greater than 0 or less than 0, will look smaller or bigger. I think example should be here or yeah, this is I think again displayed here. So depending upon yeah, this is the same thing, but here it looks smaller and here it looks bigger. That was the effect of S being greater than 0 in this here. Yeah, S is greater than 0, but the G was 400. The reflection that was used was different, and here it was different. Yeah. So you can either do with that or with S. You have to go a little bit into that locally. You have to do how it is really affecting the diffraction conditions. Actually, there is much more to it. It is also possible to find out whether it is which are the two kinds of these stacking loops, intrinsic and whether it is intrinsic or extrinsic stacking can be found out. But let's not go into the details. I think you have understood the philosophy of how it is done. Then in specific cases can always be handled. And yeah, here for example, again, this is a dark field image, wherein this is the 0th beam and this is the excited beam, and S is more or less close to 0. Now if you make that S very high, then you get these are dislocations that are seen. But with this you will not be satisfied. I mean there are dislocations, but you can't even count them. Not so useful. What they do is they change the excitation error too far away from S is equal to 0, and then it becomes more sharp. Any idea why it becomes sharp? Any can you think of why it should be becoming sharp?
I think it is close to that
Incidentally.
it is perfectly satisfying that black condition. The adjacent you think go tell us.
Yeah, I mean, but that whatever you have told will hold in this case also, in this case also. But how good it holds or how locally it holds good, that's where the question comes. And let's try to understand by this example. Let us consider this dislocation itself. If I am only slightly away from S is equal to 0, then a larger portion around this core of dislocation will be able to satisfy the Bragg diffraction condition. If my original S itself is too far away from S is equal to Bragg diffraction condition, only the most maximum tilted portion around this core of the dislocation will bring back the local material into Bragg diffraction condition. So this localization phenomena can be achieved by increasing the S value, and that's why this weak beam, this is called weak beam dark field microscopy, and it allows you to increase the resolution of your images. Here again, this is a dislocation, and I mean this is showing zigzag contrast. This is because that dislocation was inclined, and it shows it's not likely, thermodynamically not favorable that a dislocation will follow such a zigzag path. It only appears like that because of something like that inside-outside contrast that we saw. Yeah? So as the thickness is going on, so it's some dynamical effect because of which we see this fringe pattern or oscillating contrast, etc. And if you make a dark field image, then this or weak beam dark field image, the same thing looks like this. So the periodicity of the oscillation increases, but it becomes thinner and so on. Then finally, I was speaking about the Burgers analysis. So assuming that these are edge dislocations, then this G dot B is equal to 0. That's the criteria, and that actually is what goes into that Bovie-Whelan equations. So it actually boils down to that. And for the case of edge dislocation, the whole analysis is very simple or is easy like this. In the case of screw dislocation, it is not this easy. Now G dot B is equal to 0. Our aim is, let us say, to find out what is the B. B is the Burgers vector. We want to identify where is the Burgers vector. Suppose here is a dislocation, let's say A. This A dislocation, I know if I look, where is the here for example. So I make dark field images with different reflections. In this case, it is made with 0 to 2, and then in this case, it is made with 2, 3, 3. Here, this is not vanishing. Here it is vanishing. It is vanishing because G dot B is equal to 0. So I know that what is my aim to find out. I know that G1, 2, 3, 3, G1 dot B is equal to 0. I should find out two more cases which will give me G2 dot B equal to 0, G3 dot B equal to 0. Then I can solve these three equations to get three-dimensional Burgers vector. So this is the trick for Burgers vector analysis. However, this is a schematic diagram of a screw dislocation. This we have spoken of, and this was one example wherein, any stacking fault, if it is there, then it will show fringes in the image, and how these fringes come up is also matter of calculations. One has also to consider inelastic scattering effects and all that, and there are reports which say, for particular kinds of defects. So what people do is, they see this is a bright field image of the same defect and this is the dark field image, and then they see whether you have a complementary contrast, whether on the left side the contrast is complementary but on the right side it is same, something like that. And then depending upon that and the calculations, they have made some inferences, etc. So with that, one is able to find out if there is a stacking fault. Depending upon the contrast and its relation to the dark field contrast, they are able to say which part of that stacking fault image is on the top side and which part is on the bottom side. They are also able to find out whether it is a 180 degree stacking fault or a 120 degree stacking fault, etc. So these inferences can be made by combining observations with calculations and also taking help of the theoretical or literature work already published. So I think with that I have come to the end, and so if any questions, either maybe few now or later sometime. Pardon? इसका प्रिंट आउट नहीं है, but I will leave it until Monday.